Welcome back. Would you like to do some partial fractions? So partial fraction expansions, or PFEs, these are required so that we can do an inverse transform. Inverse Laplace transform. Okay. So this one here is going to have real and distinct roots. All right, so we want to find the little f of t, or the time domain expression for this frequency domain expression, big F of s, which is this thing right here. So the denominator has been factored already. But keep in mind, depending on how much you want to get involved in these, and that kind of depends on what you end up studying. Like if you go into signal processing and electrical engineering, you'll be doing this extensively. I remember many long nights studying this stuff many years ago. But anyway, there's some rules that, if you really get into it, apply. Like this needs to be a proper rational function, and this one is a proper rational function. And what does that mean? Well, it's a rational function because it's a ratio of these two polynomials in descending order, or listed in descending order. The top one is s squared, and then s, and then just a constant. So that's what I mean by descending order of the exponents. So this one has the numerator has the biggest power 2, and the denominator is already factored. But if you multiply this all together, you're going to get s cubed, right? You're going to get, if you multiply these two together, you're going to get an s squared, and then you do another multiplication, you're going to get an s cubed term. So the largest exponent on the bottom will be s cubed, and that's what you need to have a proper rational function. Is the highest power on the denominator must be bigger than the next than any power on the numerator, and it will be, because the bottom will be s cubed and the top is s squared. So it's a proper rational function because of the denominator having the higher power. All right, so that's the expression. So we can't transform it as it is because we don't know the transforms of all of these things, if they even exist. Well, I guess they will exist. But so what we do is we come up with an alternative form called a partial fraction expansion, where you just pull apart the fully factored denominator, right? Right, you just do that, and then you solve for the k's. All right, so we're gonna solve for k1. So 18s squared plus 66s plus 54 over. So the way this works is, I'm going to skip some steps here and just kind of do it in a shorthand. And we're solving for k1, so the s plus 1 term is going to go away. You're just going to have s plus 2 on the bottom and the s plus 3 on the bottom. That's because you're going to multiply through the entire thing by this s plus 1. So it'll cancel this s plus 1, it'll cancel this s plus 1. And okay, and then the other two, so you end up with this, just from this s plus 1 canceling and this s plus 1 canceling. But these two terms go away because you're going to evaluate both of these, or all four of these terms, you're going to evaluate them at the root of this thing, or s equals minus 1, the root of this denominator, which when that's on this s plus 1 term is on the numerator, it's going to evaluate to 0, which will make the k2 and the k3 term disappear. All right, so this is kind of a shorthand way to do it. You just, all right. So this ends up being 2. If you plug in minus 1 into all of these things, Yeah, it's 2. I guess I could do one more step. So plugging in minus 1 here, 18, you're going to get, because 1 minus 1 squared, right? And then minus 66, plugging in the minus 1, and then plus 54 on the numerator. And then you're going to get 1 here. Minus 1 plus 2 is 1, and then minus 1 plus 3 is 2. You're going to get that, which is equal to K1, and K1 has the value 2. This is just this identity symbol to be more proper about the mathematics. I mean, how proper should you be with the mathematics is the question. Well, as engineers, you know, we like to be as casual as we can because we're just trying to get a tool that's working. But as those tools get more sophisticated, then and the math gets more involved, and the importance of staying precise becomes more important. Okay, so this is an introductory course. Some of you may go off in different directions and never really come this way again. Others of you might go a little bit further and be more precise. It may sound like I'm wandering, but look, this is kind of an important idea, really, because it's hard to be an engineer, all right? And there's different levels of engineers, let me say. So most engineers, this is safe to say, I think, the vast majority of engineers work on problems of, you know, medium difficulty, let's say. You know, that's just what most people do. And then people tend to differentiate. Like some people will become engineers and work on these medium difficulty problems. And then some people will become mathematicians and just work on math. Now it's a rare, even rarer set of, a rare people or a smaller set of people that can have the ability to combine both of those things. And that may be you. You know, you might be that person. But I'm just trying to point that out. That's an amazing thing. The people that can do those kinds of high level math and still keep the applications together. The people that write the book, the textbook. All right. Anywho. Just moving right along. Sorry for the little wandering there. I guess you can fast forward through all of that stuff, huh? Instead of just tuning me out in the classroom. You never do that. So now we're solving for K2. So the K2 denominator disappears out of the bottom of this thing, and all this stuff ends up being K2. And then and you evaluate this at s equals minus 2, the root of K2. So you end up with 18 times 4, minus 2 squared, right? Minus 66 times minus 66, not 666, 66 times minus 2. Ooh, yuck, ugly. Just minus 1 and 1. Is K2, which is 6. Then we're going to solve for K3. So 18s squared plus 66s plus 54, and the K3 denominator drops out of this thing, and you're just left with the other two denominators, and these end up being equal to K3 if you evaluate all of these at the root of K3. S equals minus 3. And so you end up with 8 times 9 plus 66 times minus 3 plus 54 over minus 2 times minus 1. This ends up being K3, ends up being 9. So now you plug the 3, the 6, and the 9 back into this thing right here, and then you can inverse transform this. So you plug back, you plug the k's back. So big F of s is 2 over s plus 1 plus 6 over s plus 2 plus 9 over s plus 3. And then we can go back to we can go from S to T domain. We can do an inverse transform. So f, little f of T, time domain, is, so we've got this rule, right? We've got this rule from table 12.1, rule number 4. It's e to the minus at is 1 over s plus a. So this is f of t domain to big F of s domain, right? So we just have that rule 3 times here. So it's 2 e to the minus t and 6 e to the minus 2t plus 9 e to the minus 3t. And because this is a one-sided Laplace and all of these transforms are only defined from 0 to positive infinity, they're only defined for the positive half of time, you got to throw the u of t on there. That's it. This is the answer. Pretty cool, huh?